Hey everyone, today I'll be talking about a very interesting kinematics problem. And it's interesting because the problem is regarding sound, and just not a topic you usually find yourself concerned about in a kinematics problem. And it has to do with supersonic speeds. So I'll read the problem statement. A supersonic bullet at velocity v is fired from the green point along the top line parallel to the ground, which is the bottom black line. The bullet's line of fire is a height h above the ground, and by the time someone standing at the blue point hears the bullet, how far is the bullet from the blue point? And assume the bullet is shot sufficiently far away from the blue point. So in this problem, we have this diagram here, and essentially what we're given is that this green point is going to be where we start with our bullet, and the bullet is fired along this top black line, which is parallel to the ground, which is the bottom black line. And we have an observer here listening for the bullet as it travels across this line of fire. And it's asking for, by the time the blue point hears the bullet, where is the bullet? And that's essentially what we're trying to find here. So let's first label what we know. We know that this is a height h away, height h, okay? And we also know that there's a very straightforward method to solving the problem. So we assume that the person at point, this blue point here, hears the bullet from, they have to hear the bullet first. So the quickest way for sound to travel might be for the bullet to travel some distance, let's say somewhere around here. And then from this point, sound travels straight to the blue point. And how we would solve it straightforwardly, which I'm not going to do because there's a faster method, but we would do this by finding the time it takes to travel this distance. Let's say this is x. And then let's say that we know this distance as well. And this distance we can say, perhaps we can compute something using this angle theta, some other parameters here. We know that this is h. And we would have, let's say this is length y, and the time it takes to travel here, let's say the bullet speed is v, which remember is supersonic. So that would be x over v is the time it takes to travel here, plus y over c, where let's say c is the speed of sound. And this would be the time it takes for sound to travel, given the sound emanating off of the bullet at this point x. And the way to find the best, most optimal path for time would be to differentiate this. Let's put this as total time, dt versus one of your parameters, either dx or d theta. I think d theta might be a bit easier to do. And you would find this, set this equal to 0, and that would give you the theta for which this is optimized. And so this is one method you can do it, and this requires a bit of calculus. And it actually gets rather nasty as you progress with your calculations. You might think, because we have this trigonometry and a whole bunch of other really terrible equations to handle. So there's a much easier way to approach this problem, and we're going to do that by looking at what shockwaves are. So if you've seen any videos or any diagrams of supersonic objects traveling. Let's say you have a bullet traveling along this line at a supersonic speed, and the bullet is right here. If you know about science, you know that it creates shockwaves, and these shockwaves are actually made of sound. And what is actually happening here is, let's say the bullet was previously at this point. Now, at this point, the bullet emits sound from traveling this point. However, because the bullet travels faster than sound, by the time the bullet travels here, the sound in this direction will have traveled less. And in fact, since sound is on the same speed across this point, it actually creates a circle or a sphere in 3D of where the sound actually is. And the reason I drew this tangent here is because this is actually a special property we can see. So let's imagine that from this point to this point, a time t1 has elapsed. So we know that this distance, let's draw this here, this distance right here is v times t1, because the bullet in this t1 has traveled this distance. And furthermore, we know that because t1 has elapsed, sound traveling from this point where the bullet had first been has emanated a total distance from here to here of ct1, all the way to here. And And it's basically unique because this is the radius of the circle. So if we were to draw this radius, make it tangent here, well, we draw the tangent line here. We don't know that this is a shock wave yet. This is a tangent line. We have some angle theta. So if this is CT1, and this is the hypotenuse of the right triangle is VT1, we actually know from this that cosine of theta is equal to C over V. That's because the T1 and T1 over here and T1 over here cancel out. And we can do this further by, let's say the bullet had been over here. Now, at this point, let's say it took time T2 to travel from this point to this point. Now, in this distance right here, this is VT2, my bad. And the distance that sound traveled from this point is CT2. Now, you know that the ratio right here, CT2, this is also theta, because the ratio of C to V is still there. So in fact, we actually got that all the circles produced by sound actually lay between and are tangent to these tangent lines. So they all share the same tangent line, and we have similar triangles, this triangle here and this triangle right here. Now, this makes it very easy for us to compute where sound is traveling optimally, because as the bullet travels, a wave of sound is being produced along this tangent line. So how does it relate to our old problem? Well, let's look back at our diagram, and I'll give ourselves some more room. And let's take a look at this. So let's say the bullet had now traveled to somewhere over here. And let's say the angle theta, which remember is equal to, cosine of theta is C over V, so this is equal to the inverse cosine of C over V. Now, let's say this theta allows it so that at this point, exactly, the shock wave of sound produced by the supersonic bullet exactly crosses our blue observer right here. Now, the sound that actually reached here we know is tangent, which means the bullet, while it had been right here at this position, emanated sound, and the bullet had traveled to here while that sound traveled to our observer. And that's the first time sound reaches the observer for the bullet. So all we are left to do is to find this distance right here, and we are done. So how might we do this? Well, we are given, first of all, that this is height h. Let me relabel that. And we know that this angle right here is theta. Now, furthermore, let's see that. Let me show you this theta. So that's theta. We have theta over here. It's just the opposite direction. And now we have that theta, cosine of theta is C over V. We can draw our height here. And let's use a little geometry trick here. If this is theta, by similar triangles, this angle right here is also theta. So if we use cosine here, we have our adjacent over hypotenuse is C over V. And that means that because this is height h, remember, h over this hypotenuse, which is, let's call this a mystery L. So h over L would be equal to cosine theta. L, the length we want to find between the blue observer and the bullet by the time the observer hears the bullet, is thereby h over cosine theta. We plug this in, and you get that VH over C is going to be the distance from the bullet to the blue observer. And that is how you find it without using calculus and just simple geometry tricks. So what's the takeaway behind this problem? You know, there were a couple key facts that we exploited to come out with this very simple solution. The first one is constant velocities. Throughout the problem, there were no accelerations. This allowed velocities to be constant, meaning that we could analyze it using the time the bullet traveled here versus the time sound traveled here. And this gave very nice geometries in the form of a shock wave. And this is a very nice lesson to learn because constant velocities will often end up in very nice geometric patterns. And we can take advantage of that by looking at similar triangles and other things in our physics. And another very important lesson here is don't immediately go with the most straightforward solution. Remember, the most straightforward solution required calculus, and was actually very nasty to do, versus this very simple one, if I had explained it less, would have taken a lot less time to compute. So a lot of times, don't always try the most straightforward route. It may be more beneficial to look and see if there are some nice patterns or interesting shapes for us to analyze in physics. And thank you for watching today's video, and as always, enjoy physics.